doubling?
Yeah, sure.
Okay, so I guess today we're going to talk about, what were we talking about? Performance? Methodology, mostly methodology, but you know, as with all things performance, you really can't separate you know, yourself from tools and a little bit of talking about technology. So we're going to get into that today also when we start looking at specific problems. But I think the primary takeaway from this particular talk, as far as I'm concerned, should be a way of proceeding through a performance tuning exercise. And with that, I can say that Aleksey has, I guess we're primarily going with his mind map. I've created my own mind map also, which is very similar to his, but I think we're going to be talking about, like, okay, how do you enter, right, and how do you proceed through? You know, what are some of the tools that we can use, and what are the signals that the system is giving us that we can actually use to decide how to proceed through this particular exercise. And with that, go to the next slide. So this is Aleksey, and what do you got? 7+ years of Java. Well, this guy has been working on Hotspot and performance tuning Hotspot. So the reason why your applications in Java actually run as fast as they do is because of the work of, well, what he's been doing. And I see for projects you have Harmony, which now that you're working for Oracle sounds kind of like really amusing.
Yeah. I'm not working on that anymore, right?
Right, yeah, okay.
So I joined the other clan.
OpenJDK, do you have commit status now too? They let you have commit status?
Yet.
We were talking about commit status this morning, saying, like, you know, if you only can potentially break the build, then you're probably not going to get commit status. But if you absolutely will break the build, then you're up for commit status. I don't know if you saw the workshop this morning, but they had fun getting that build to work. Spec JBB 2000
and something.
And something.
It's now 2013.
Is it really?
Yeah.
Okay, we'll have to take a look at that. Anyways, you can look at his projects there. Me, as I usually like to say, you can just Google and find, well, both of us anyways in there. So performance tuning, we mostly do a lot of just performance tuning for customers and teach people how to performance tune with this nice performance tuning seminar. And recently, what I've done is with a couple of other people here that you might have met already, Ben Evans and Martin Vorberg, is that we started a tooling company called JClarity, and we should be sometime this week just able to release a beta of our first tool. So this is really a new joint effort. We might get a look at it later on during the talk. So you know. We have this program, Friends of JClarity, which you can go and visit and find out about. In terms of my performance training course, twice a year, we end up at Heinz Kabutz's place. I don't know if you know him, but he's a fellow Java champion and, well, really a concurrency expert. And so we end up at his place and we have a performance tuning course offering. Does that seem cut off to you?
Yeah, it is.
It is. Okay, so that's quite correct.
It looks nice this way, but
yeah.
So I'm sticking with this.
Looks good on my machine.
Yep.
Right. Works on my machine. Yes, that's perfect. Okay. Yeah. Okay. So in June, I think is when we'll actually have the next offering of this. Right. So this is our standard disclaimer. We have any resemblance or opinion or recommendation made during this presentation of performance tuning device is merely coincidental. As I said, advice given at a conference is not a substitute for common sense. So we're going to tell you a bunch of stuff, but you really have to understand that performance optimizations are really responses to highly localized conditions. And if your locale doesn't look like my locale, then anything I'm telling you might not work. Now, hopefully we can get around some of this with the methodologies, but anyways, you have to go and kick the tires on things. As you'll see during the presentation, even Aleksey and I won't agree on everything, will we?
No, we wouldn't.
Absolutely not. That wouldn't be on. Okay. So really, what we do want to suggest is that we want a hypothesis-free investigation of performance, right? So we'd like to, and this is where we actually differ in our experiences. I go into customer sites. I've never seen the application before. I have no idea what's going on, right? And that's the situation I have to deal with. So it's not only that, I don't want to make any hypothesis about what the problem is. I can't because I have no information, right? The only information I'm getting is from taking a series of measurements and then progressing through a series of steps in order to eventually arrive at a solution to the problems. And I found that this is a very effective way to progress. And I think that we'll see with the mind map that we have here today that it sort of follows the same flow in the sense that it's top down, and it really can really be hypothesis free. We don't have to know or guess what's going on. We're just going to take measurements and then flow through this mind map in order to finally arrive at a conclusion.
Right. So the talk that we are getting here is actually the blend of two talks. One of the talks that I have in Russia in Russian about the performance optimization methodology, and it's more or less academical, very dive deep stuff there. And the Kirk is actually like to do the demo stuff. So we try to merge these talks together. So this talks is going on the two stratums, if you want. First one is rather basic, which could be interesting for those guys not experienced with performance at all. And the second one is more deep dive into the particular performance issues that you might probably having. So if you are finding yourself puzzled over what we are saying to you, just stick with us. We will get back to the basic stuff.
Or better yet, ask a question.
Yeah.
Right?
All right. So we usually start this talk by saying, here we are, the software engineers, born on the field of computer science, when we have all these abstract things that we construct our software on. We have the abstract machines, we build the abstract frameworks processing the abstract data, and it's very tempting for us to think it wouldn't end. We will build the very perfect data storages, we will build the perfect business logic, we build the perfect presentation layer, and this all will went just fine. Our job starts when you are meeting the real world. When you start to run your applications on the real hardware, on the real implementations of the frameworks, and you start to pipe the realistic data through that stack.
Right. And so what you find with realistic hardware is that we have finite capacities, and we don't have an infinite supply of this thing.
Yeah.
So.
And the important thing is that if you are trying to model or predict in advance how that whole stack would interact with each other and try to derive the conclusion from that, you will fail miserably because the interactions between those layers are so complex, you wouldn't get any accurate model that you can still comprehend. So we bail out of that and actually say that we are basing our performance research on the empirical evidence, that we don't want to build the analytical model of the system, but rather we want to build it from the bottom up. We want to build some model that corresponds to our measurements or our empirical evidence of how this system performs. So that takes us to the benchmarking. So when we do the performance analysis, we need some isolated conditions at which we can then use to derive some meaningful data from it. And we do that by setting up the experiments. The experiments is the ultimate tool for getting the empirical data. So for the experimental setup, you can't go for performance without proper test environment. And by proper test environment, we usually see that the test environment should be relevant. It should measure the phenomena you want to test. It should be isolated. It shouldn't really measure anything else. It should be measurable, so you can actually derive some knowledge from that. It's useless to run the test and not getting any knowledge out of it. And it should be reliable, so it should be reproducible from run to run in order to get the consistent result, so that your results are comparable when you change something. And I think we get back to you.
Yeah, all right. So in terms of being relevant and isolated, The issues that we typically deal with is, we have to deal with hardware. As I said before, hardware, we don't have an infinite amount of it, and it all has finite capacities and finite throughputs. And so if we're running an application, and properly performance testing it in a piece of hardware, we really want that test to to mimic what our production systems look like. Because if we don't, if we have different quantities of hardware, then we can actually shift the bottlenecks. We can create what I would like to call phantom bottlenecks, right? Things, consider it this way, right? If you change the configuration of your network, so you suddenly have much less network in your test environment than you do in your production environment, then it's potentially that you could shift the bottleneck onto your network, and thus hiding the problem that you have in your, in your production environment. So then you can't even find the problem in your test environment. And there's a whole other situations that you can run into that are basically going to shift the bottleneck from where it is in your production system to someplace else, or potentially just make it go away altogether so that you just absolutely cannot reproduce it. The other thing we find is that we want to test on a quiet system, right? And this has to do with isolation. If there's other things going on the machine, then it gets really hard to understand. Is that the effect of the other thing, or is it the effect of something that our application is doing? And it gets very difficult to tease these signals apart and then make a proper diagnosis. Relevant in terms of software. Well, we're going to need a whole bunch of things to help us here. We're going to need a test harness, for instance, right? And that's really the combination of a load injector and something that's going to accept the output of that particular load. Maybe you have to wrap your application in some sort of acceptor to accept the traffic that you're trying to generate on the application, that you're trying to push on the application before you try to tune it. Right, so, and those things all have to work very nicely, or you can run into other issues that we'll talk about. In terms of data, again, this is under the category of relevant. We need our data to be production-like in volumes, which means that if we got a 10 gig database, then we probably should be testing with something along that size. And the data should look like our production data, right? But this isn't just the data that's actually feeding the application. We have to think about the data that's feeding the test harness also, right? That data also has to look like data that you receive in your production environment, and it has to look that way in terms of volumes and in its content. And the reason why we want to do that is because a lot of systems use caching, right? And if you want to make your application run really, really fast, then we all know we use cache, right? But if our application isn't spilling cache at the same rate that our production system is spilling cache, then again we have another situation where we can have phantom bottlenecks, or in this case we are just not going to see a bottleneck because we're unable to exercise a particular execution path fully, right? We'll, the cache will just truncate that call and just return the result. And that's one of the problems we actually had setting up our benchmark. So we had to do a little bit of funny simulation in the benchmark, right? But the cache on your machine was like, I think Oracle buys you, pays too much for their hardware or something. I don't know what it is, but
no, it's not.
Yeah, there's enough cache on this thing that we had to work around it in order to get a reasonable demo. In terms of measurable and reliable, so we're going to take the load test harness, and what we're going to do is we're going to script it so it's going to do things. These are things which I call usage patterns, and a usage pattern is like a use case, which I think we're all familiar with, but we need to add more information to that. We need to know the depth, the breadth, the velocity, right? So what's the transactional rate? How many people are actually engaged in this particular transaction? How fast do they progress through the use case? And what we wanted to make sure is that we can program our load test harness so that it actually mimics all of this behavior. Because if we don't get this right, then we don't apply the right pressure onto the application. If we don't apply the right pressure onto the application, we're not going to apply the right pressure onto the JVM and consequently not going to apply the right pressure on the hardware. And if we don't apply the right pressure on the hardware, then all of a sudden we have a problem that we're going to shift or miss or somehow otherwise start trying to fix things that we don't really need to fix. Okay? And that part is really freaking hard.
Yeah, it is.
Really hard.
Really hard.
Yeah.
The performance is even harder, but this is really hard.
Yeah. I would almost say it's the other way around, but, you know, we'll let it go at that.
JDK is simple to set up. Customers' applications aren't.
Absolutely. That's the difference in our experiences then, I guess. Performance requirements. Before we start any engagement, I want to know how fast the thing has to go. Or I get a job like his, where it's just the requirement is as fast as it possibly can be, right? Which is really good. So my performance requirement is as fast as it needs to be. You know, so what is that? Well, that's a requirement, a non-functional requirement. And it's also the trigger metric that we're going to use in many cases to determine if we have to performance tune an application at all, right? Performance tuning is about improving the user experience. That means making it more performant so that the application performance isn't in the way of how the user can interact with a particular application, right? You know, we want to take that condition off the table so they can just work, right? So we'll set performance requirements like that, and if we're not meeting those requirements, then we trigger a performance investigation. You know, last point here is on validation. You know, a number of times, all we've done in a client-side engagement is fix their test harness. It was busted. A busted test harness means we weren't able to apply load on the machine or on the application. That meant they weren't able to prove that they were meeting their performance requirements, which meant that they weren't able to release. In some cases, this would go on for 2, 3, 4 months, trying to figure out where's the bottleneck in the application. Where's the bottleneck in the application? Well, it's not in the application. It was in the test harness. Test the test. Make sure the bottleneck isn't in the test harness. If it is, figure out a way to get it out of there. And there's all kinds of other tests that we actually do to the test harness. For instance, we might stub out the application altogether and test the test harness and make sure that, we're getting timing for that. Should be 0.
Yep, or close to 0.
Or 0.
All right.
Not yet. Stand over there. Go away.
Right there?
Yeah. Okay. So testing steps are going to be, so we're going to script the usage pattern into a load test, install, configure the application, and hopefully our hardware and our installation specs and everything is going to be the same as our production environment. This means on the question of virtualization, if you virtualize for production, you virtualize for test. If you don't, you don't. Okay? Whatever the choice is there, make sure you follow it in your testing. I know some people like to virtualize their test because it really helps with the admin process, but virtualization interferes with how you interact with the hardware, and that will cause other difficulties. Set up monitoring, that's when you get to talk, right? Mm-hmm. You can talk about all that stuff. Performance requirements, we need to know what they are. And so we're going to have something that's actually going to monitor for compliance. And then we're also going to look at some, what I call key performance indicators, things that are going to let us enter the performance tuning engagement at a reasonable place. Kill everything on your system, all your virus scanners and all that other stuff that doesn't run on your production system, that might run in your test environment. Then we'll spike test it to ensure correctness. So just do a quick run, make sure that no bits fall off, the environment looks good and everything. And then we'll move to turning that into a load test where we'll actually put the application under load and we'll take the measurements and then we'll take those results, validate them, make sure that they are actually good results. We don't want to be acting on bad results. and then we'll use those results to try to identify what the next step is, and we'll just keep going through this test, validate, next step, possibly fix, and we'll just go through that loop as long as possible. Yes?
Let's start our hands there.
Demo. Okay.
So this is our mascot there, which will highlight the demos, which I think is appropriate here. So we have a very simple web application. It is deployed on Jetty, so we can actually navigate through localhost. Oops, that's probably not right, right? Yes, we failed the demo. That's right.
Failed the demo right at the beginning.
Okay,
that was our sacrifice to the demo gods.
Yeah, just bear with us for a moment. That's data. No such data. Nice.
Okay.
So we can talk about something else in the meantime, as you always do in these talks. Where's my flash drive?
So, yeah, I think it's DevOps is better in November than December because of the weather.
All right.
Not quite what you're thinking about? Okay. So what he should be doing right now is
I am doing that.
Is getting, while we're getting our web server to run, is the other things that we want to look at is we want to make sure that there's as little stuff running on this machine as is possible, so that we don't have any interference from other applications, right?
And that was the example of the spike test. I didn't proceed for performance test without actually figuring out whether my application works.
Yeah, well, this is just a consistency check. We actually want to run the test with JMeter, right, with our harness.
All right, so,
we'll spike it.
We actually have this load tester there, which is Apache JMeter, so you might probably find that familiar. We probably run it with 1, right?
Yeah, and probably move that 150 down to 1 also.
Right.
So, well, it looks like it finished anyway, so it's okay.
Right.
Okay, so it looks like everything's working on here. We didn't get any errors or anything, so everything functioned. We got a nice response time of 289, average response time of 289 milliseconds. Which reminds me, did we get a performance requirement here?
Not yet. Do you want to set it?
Yeah. 1 millisecond? No, we'll say 100.
Say 100. Okay.
We'll say 100 milliseconds, and then we'll see what you can do afterwards.
Right.
Okay.
So that gets us back to the metrics, right? Once we introduce the test, we need to figure out what we would actually measure, and what the things that we measure are called naturally metrics. There are several types of metrics that you would like to measure, but most of them are folded into 2 distinct, maybe distinct cases. First one is the throughput or time metrics. You can also meet them by the names of bandwidth or latency. So the first one is actually saying how many operations are done per time unit in some significant time interval. And the second one is how much time one single operation took. And the throughput is actually very easy to measure and very easy to interpret. The latency is not that easy to measure correctly. It's not that easy to reliably infer anything from the latency, because in the throughput you have like average throughput and you're done. For the latency, there is a significant difference between the average response time, the response time in 99th percentile, or the minimum or the maximum response time. So you have to choose your metrics carefully there. It might be tempting to think about these 2 metrics as the distinct ones, but in fact they are related to each other. This is the sample chart that we have in one of our benchmark. This is actually the upcoming Spec JVB 2013, which tries to analyze how the response time and throughput interrelate together, right? So on the y-axis there, I have the throughput, which I incur on my system. And on y-axis there, this is the response time that I got on my responses. So there are different things to munch about this graph. First, note that the y-axis is logarithmic. So the difference between response times at the lowest throughput possible in that system and the response time at the highest possible throughput in the system is really, really big. So it's like several orders of magnitude there. That actually brings you the interesting observation is that if you want to get the low latency working, this is probably not the time you are pushing for the highest throughput. So you want to have some headroom for your system to actually fit into that latency envelope. And the vice versa. If you want for the highest throughput, this is probably the time when you should start to consider dropping the latency requirements off the table, because that will drag you back.
There's some queuing theory behind this, isn't
there?
there?
There's the queuing theory behind it. So this is generally true for the queued systems. When you don't have the queues or try to not to use queues as much as possible, like doing the busy loops instead of blocking on the queue and all that stuff around, you will have another graph there. But if you will look carefully, it would appear as if this graph is just cut in the middle there, and you are not reaching the highest response times you can get, and paying for that with your throughput. Right? So the queuing theory behind this, there is the very nice observation which has the name of Little's Law, which tries to connect the throughput through the system and the service time for the requests of that systems and the number of outstanding requests. So it's a little, very simple but beautiful relation. And it doesn't really depend on the distribution of the arrival rates, etc. This law has two significant implications. First one, if you stick with the particular L, which is maybe your concurrency level, meaning the number of workers that actually process stuff, or the length of the queue at which you accumulate requests, if you stick the L to some constant value, then your throughput is inversely proportional to response time at that point. So if you have a lot of work, so your response time is high, that automatically means your throughput is low, and vice versa.
Yeah, it's like if your response time is, or your traversal through the critical section is 10 milliseconds, it means you can only have a throughput of 100 transactions per second.
Yep.
Right?
Right.
So, and if you can bring that down to 1 millisecond, then all of a sudden you have 1,000, right? So you can see how this is actually very important. And this is a law that actually regulates a lot of our everyday life. For instance, how fast we can get out of this room.
Yep.
As an example.
Or how fast you can get your sandwich.
Or how fast we can get our sandwich. Right, all kinds of different things.
Right. So the other implication, which is more like design one, if you know the average arrival rate, that throughput thing, and the service time, you can actually infer how much headroom you need to store all these outstanding requests, which is useful sometimes for design of the systems. Now I have a pop quiz. So imagine we have the application in which we have two distinct phases, part A and part B. So part A takes 70% of the time, and we know by just wild guess that we can speed that part up 2x. So we can cut the execution time of that specific part 2 times. And the part B takes 30% of the time, but the potential speed up there is much bigger, and we know that, again, by educated guess. So imagine that you don't have time to fix both parts. Which one you should invest first? Who's thinking part A? Okay, thank you. Who's thinking part B? Who thinks don't care? Who's the manager it just needs to get the job done?
Yeah.
All right.
Who doesn't know how to raise their arm?
Oh.
Okay.
Right, so if we do that graphically, we might notice that optimizing for part A is actually beneficial because there I have 65 seconds, and if I optimize part B, I have 75 seconds. We can actually generalize that observation and come up with this guy, which is called Andals Law, which says, okay, if I know the size of the part that I'm optimizing and the ratio for which I can optimize that part, I could actually infer the speed up for the whole application.
Oh, wait a second. Isn't Andals Law about serialization?
Yeah, it was first constructed in the terms of the parallel computation, but this construction actually applies not only to the parallel stuff.
Ah, okay.
So the important implication of the Andals law is that if we draw that function in some specific coordinates, so for instance, for under axis x, we actually have the part that we are optimizing. So 0 means we do not optimize anything, and the 1 means we optimize the whole application. And the axis y is the total speed up for the application. And the colored lines are the speed ups of that particular part. So we can figure that if our part that we are optimizing for is actually small, so for instance, let's pick 0.3, like 30% of the application, we can actually speed up there. You might see that no matter how hard you try to optimize that part, the total speed up for your application would be actually not that much. So this is the law of diminishing returns coming back and strikes us again. And in realistic applications, finding the piece of 30% that you can actually optimize is very lucky. So that means you probably should not expect that you will fix something in your application and you magically have 20x boost. If that's something happens, that means that nobody else have looked at the performance of that application before.
Yeah, it's really low-hanging fruit.
It's really low-hanging fruit, yeah. So as you reap all these low-hanging fruits, you are stuck with the optimizations which can give you 1 or 2 or 5 or 10%, but not much less. All right, so if we apply the Andals law to this, we can actually get the numerical boosts there. So optimize B gives us 33% of the performance boost, and the optimize A gives more than that. That's it. It's tempting to think that if I have this Andals law and I know how where in the application I spend the time, and I know by some wild guess how can I optimize this specific parts, I could actually get the estimations for my time budget of how much time I will spend optimizing the application. However, it's not really working, and it's not really working because of this. We all learn in the course of the computer science that one of the cornerstones of our job here is the notion of composability. If you have two functional blocks, A and B, if you execute them together or execute them one by one, the result is probably not changing. They are not interacting with each other unless you explicitly build them that way. So this is called black box abstraction, which kind of isolates you from concerning the functionality of the block from the functionality of the environment.
Right. So, and that said, if I can go back and revisit this particular slide here, we often find in the real world that this time budgeting information is incredibly important when we start when we want to know where to aim our efforts, right? And this information is generally fairly easy to collect in a real application. We can simply get it from logging transactional durations.
Right.
Yeah.
So for performance, this doesn't work because we can't really say if we execute two functional blocks together, they yield some composition of the performance of the individual blocks. We can't really tell. We can only tell that we can only measure it afterwards and say, okay, that makes sense. But not the other way around. We couldn't actually predict how they operate. And this is actually why the performance is so damn hard, because you can't predict all these interactions between the blocks. So if I optimize one particular part of the application, it doesn't really mean that the other part of the application would stay the same. It could change because I had affected by the changes that part that I'm optimizing. I changed the environment or some other conditions in which the other part of the application revolves.
Yeah, our practical experiences on that is that sometimes we've optimized part of the application which has put pressure on another part of the system, that actually resulted in an overall de-optimization of the system. So the system ran slower after we removed one bottleneck, because we were able to put more pressure on something that was more critical to performance. So in those cases, we've actually had to, in some cases, just completely back off of our original optimization and take a different tact.
Right. So we get back to our demo there.
Yeah.
We had the spike test.
So let's run a full test, yeah?
Yeah, so let's try the full test. Actually, speaking of the good hardware, the full test. Actually, speaking of the good hardware, I need to do something like this before I do this. Otherwise, it will overheat. All right.
Nice.
So
okay.
I will shut down everything. I will start it over.
Yeah, so another thing that we tend to do is we want to start from a known point, which means we'll shut down things and reset things and then start from that known point. So we want to make sure that our tests from run to run are comparable. And in this case, we're running 1,500 transactions through the system over the period of 150 seconds, so 2.5 minutes. So not a realistic benchmark, but normally I run them for like 2 hours or longer. But I think for this case, I think it's good enough. Are we okay? Yeah, we're okay. So it looks like we're beyond our 100 millisecond time budget for this. We're at 140, 150.
But is it really reliable? Will it still the same?
Well, but I think since we're beyond, we can probably start looking at,
Yeah, so let's do the proactive step and say, okay, while this guy is running, we are going forward and start our
since we've already blown our time budget, we might as well start trying to figure out what's going on. So we should be looking at some of the
miser stuff. Right.
Okay, now that's really going to mess with everything.
Yeah. So we should probably pick here. If you run this application long enough, we will notice that the old gen occupancy is actually growing, and there is nothing we can do about it. So even if we bash it with the full GCs, it doesn't really go back. So what do we do with that?
Oh, so heap's filling up, right?
Yeah.
So you notice so let's take a look at this particular graphic here and sort of get a little bit of an explanation, right? Let's focus on this part over here. So what we're actually looking at here are all of the memory spaces inside the JVM, the memory pools, right? So here's Eden. This is where objects are created. So you can see recreate, recreate, recreate. It's a sampling view. And then as soon as it gets full, we're going to garbage collect it, which means we're going to evacuate these objects someplace into one of the active survivor spaces. Right now it's S1. And it looks like something halted there for some reason, but it doesn't matter.
That's full GC.
Oh,
but
there's a full GC. Okay, fine. Okay, so now S0 is now active, and you see we're going to flip back and forth, and eventually the surviving objects are going to be pushed out into old space out here. And as we can see, what's happening is that old is filling up and up and up and up, and finally it's just going to end up in a
out of memory error.
Out of memory error, right?
Yeah.
And
this is a very large machine. It's the heap size is 4 gigabytes. So.
Oh, how'd that happen?
Yeah.
That's why we didn't get the out of memory error when we expected
right,
it.
but I can push for full GC and see that the.
Yeah, so if you look at the blue line here, right, that's going to be, it's cut off, right? That's heap used. And the orange bit is heap size. You can see it's constantly going up and up and up and up. And there's some other things we could look at that basically suggest that we're putting more and more pressure on memory, so performance is going to get worse and worse. What's our performance like now from JMeter perspective? Although you've been mucking with it, yeah, we're off the charts, right?
And we also have the non-zero error rate.
Oh, look at the error rates. Yeah, we're hitting errors.
We're blowing up our validation.
Now it's possible that this 4 gigs isn't enough for this particular application. So the first reaction to this is generally to make the heap bigger. How big, we don't, it's difficult to say. We can use some metrics to determine that. But it's safe to say, in this case, what we actually have here is a nice little memory leak. So do you want to go find the memory leak?
Yeah, I could do that my way. Your way is different. All right, let's go my way. So I actually run that test before, and I did had the heap dump. Yeah, you want to say something? Just say it. Don't look at me that way.
Your way?
Yeah. This is my way. I usually get the dump from that application. And knowing what application I'm dealing with, I could actually see whether what's in there in the heap actually corresponds to what I think about this application.
What you think about the application.
Yeah.
So you're making a hypothesis then, right?
Yes, yes.
Ah,
I'm not
okay.
the hypothesis-free as you might think I am.
Okay.
All right, so if I see the heap dump there and I see the Dominator Tree, which is the...
sorry.
You want to explain this?
The Dominator? No, go ahead.
Yeah, right. So the Dominator tree, you can think about it as the tree of reachable objects. So you have the root, which is the ultimately reachable objects from outside, and you actually can build the tree of the reachable objects and then estimate how much memory is held by that root. So if we look at this heap dump there, we will find that we have lots of session objects. Each of that session object retains something around 15 megabytes of heap.
Wow.
We can dive in and see if this is actually some sort of the hash map there. Okay. And it's really small, meaning it only has the place for 4 entries. And the entry there is...
Another hash map?
Yeah.
It's a crumb trail.
It's crumb trail.
All right, whatever that is.
Right. So we can go into our code there and say, idea, wake up. Wake up.
Right. So just getting back to this notion of a Dominator tree, what a Dominator tree says is that I have a very narrow path to something that's holding onto a huge chunk of memory, right? And if you know your application well enough, then MAT is a good choice, right? If you don't know anything about the application, what you find is that MAT is actually making a guess. Now, it's a very good guess in many cases, but it's still a guess because it can't tell the difference between cache, right? Because that's what a cache looks like. It's a very narrow path to something that's holding on to a lot of memory. And so it can confuse a cache as being a memory leak. And, so you have to go through what it thinks are memory leaks and then finally decide for yourself what is the real memory leak by just investigating. I prefer a more precise hypothesis-free approach where I actually don't have to guess. And as soon as the tooling starts working,
and you call it fast hardware? I don't think so.
as soon as is this Oracle tooling or?
No, it's
not.
It's the Oracle hardware.
Right. It can't
Not
be
to say that Oracle servers are bad.
It can't be Oracle tooling, right? Because it's Oracle tooling.
Oh, come on.
Always works.
Surprisingly, how many times we actually tried that before the talk, and it works, and it never works here. So it's crumb trail. This is, by the way, the hash map which is leaking, and we can actually see what method puts the data there, and this is add crumb. So we might as well find the usages of it.
Okay.
Yeah, and we will see the 2 usages. Let's pick on this one, and this is some object called trail, which is there in the session attribute, and we adding up something there. So this looks like a memory leak, or maybe that's a caching, right? So we might want to look through this code and actually figure out whether we need that statement there. For the sake of clarity, we would say that this is a memory leak. We wouldn't go ahead and explain why. So we might as well delete it from...
No, don't do that, because it's my turn now. You've had your say. It's my turn.
Okay. Do you want to leave that uncommented?
No, do you want to put the slides back up? Leave that uncommented, yes. Yeah. Okay. So, let's talk a little bit about this. Generational counts. Okay. So first off, what we have to recognize is, what is a memory leak? Well, it's an object that is no longer semantically useful to our application, but we're still retaining a reference to it, right? And these things really only get critical if we can continue to make more and more and more of them. And that's when we consume all the memory. So what I want to do is I want to get a measure of which objects are being retained, and we're getting more created of them, and that's known as a generational count. So for that, we can get a few definitions. One is, we have to understand, what is the age of an object? Well, in this world, it's the number of garbage collections that you survive. Okay? So what's a generation? Well, it's all the objects, right, of the same class of the same age. And a generational count now becomes, right, how many different ages does a particular object, class of objects live in? So if we look at this particular chart here, right, you know, the question is, if we look at circles, for instance, what's the generational count of circles? Well, it's only of age 1. There's not in any other age here in this a very abbreviated list. So I'm going to say that circles have a generational count of 1, where they happen to be of age 1 also. If we look at clouds, right, they live in 2 different ages, so their generational count is 2. So let me holler out a shape, say triangle. You guys holler back what the generational count is. 1. Yeah, it's really easy, right? Really, really easy game, okay? Cross. Our half ellipse. 1. Our stars. So here's my assessment of the situation based on this measure. Right? Based on this measure. Right? Circle is normal. Cross is normal. Ellipse is cached, but normal. Triangle, normal. Cloud, normal. Star is a leak. Right? But fits our definition of a leak.
Yeah, but why is the half ellipse actually cached? It had survived 4 garbage collections. So why?
It might be a leak, but I'm going to guess cached. Because think of our caching patterns. We load a bunch of stuff at the beginning, and when we start the VM up, and we leave it in the VM forever. That's one pattern, right?
Yeah.
Okay? We don't create any more. If we created more,
or
then
maybe
that would be a leak.
Yeah, or maybe our cache is actually getting dried back, and we replenish this cache as we go.
Right. And in that case, you cap the number of generations that the object lives in. So it has an extended life cycle, but it's still not tied to the number of collections, right? Where a leaking object is going to have a generational count that's often equal to the number of times its number of collections that have run. Okay? So now we have a very precise definition of what a memory leak is, and I don't need to know anything about the application to identify a memory leak. As a matter of fact, we're doing it with these things here, right? There's no context here.
So how do you get that information from the application?
From an Oracle tool. I find it very funny. You're using the Oracle guy is demoing IBM tools, right?
I got mocked for that.
Okay, I'll let you drive if you want.
Right. So now that we had fixed our test, and believe us, we fixed our test now, and it is reliable. We want.
Well, we need to show, right?
All right.
Of course, they need.
All right.
Of course, they need to see this. Because that's why we left it uncommented, right?
Yeah. Well, I just commented.
You had your turn on the tooling. Don't be nasty.
It would get some time to actually do that. So I would just run it and leave it running. And
yeah, just throttle back a bit because we want actually things to develop there. So you have Visual VM running first? Let's get Visual VM running.
It is running.
Okay. But hold on.
We can actually close it down there and say, okay.
Yeah, okay, let's start over again, yeah?
So,
Did you start?
So it's running.
Yeah, but we didn't get our profile started here. So let's go to attach to the, Jetty.
Jetty.
Okay, profiler, settings. Okay.
Thank you.
Now we need to get the garbage, this profiler has to interact with, no, not that one, that one. Has to interact with the garbage collector, and that's the setting that will do it. And we want to record the allocation stack traces too, because we need to find this thing afterwards. Okay?
All right.
So attach it. The only problem is you're already running, right?
Yeah, so it might mess up.
It's okay. Just get rid of the settings there if you don't mind.
All right.
And there we go. Okay. Now, what I'm going to look for here is I'm going to look for a carrier. Right? JDK classes don't leak. Something causes them to leak.
Presumably, not leaking?
Presumably, an application-specific class, right? So what I'm going to do is I'm actually going to look for a carrier here to see if one shows up.
It was trail, right? Crump trail. It isn't there. It was storing the strings there.
Yeah.
And it's not there. So we are fine with it. And we actually, if we go and look for the heap profiler, the heap statistics, we can actually see that the live data set is actually really small. So after the major collections, you have...
Oh, so you've already fixed the bug then?
Yeah, right.
Okay, so let's go back to the profiler here, because I want to just show one thing for sure, though, is we sort by generations on the generation column here. That's what we should do, right? What we want to do is oh, it's cut off. Can we slide that a little bit over to the right there,
right,
so that we can actually see it? So we want to look at what that generation count is, and generally what we'll see is that the generational count of leaking object will be enormous. And as you can see, these are all mostly, this is a normal distribution of a healthy application.
All right.
Thank you.
So you're happy? We can proceed?
Sort of, except for we didn't actually show how to use the allocation stack traces to avoid all that analysis that you did. So by getting the allocation stack trace, we're actually getting the causal execution path for that object being created. And from that, we can actually sort out who's responsible for creating the object. We can look at the point of binding by looking at the heap dump down and using a heap walker to understand the reference interactions. And from there, we can combine those bits of information to actually understand the application logic that's causing the leak and create the fix.
All right. So now that we had figured out our application is, and the test is actually reliable, and it is reliable.
It is reliable, yeah.
Now we turn to the performance questions, and we ask ourselves, how do we speed up the application? Well, the question is really obvious. You have to change something somewhere in some specific way. This is the correct answer to that question. And yeah, that's kind of obvious, right? So, but we can actually leverage that question and try to unfold it into the parts. So we
Is it really that obvious, though?
It is obvious for me.
But
it's pretty generic.
It's only obvious if you get the right measurements, though.
Right.
You know, if you don't have the right data, then you're going to generally be scratching your head trying to sort out what's going on.
Right. So if we decompose that question into the three distinct pieces of saying, what should we change, where should we change it, and how should we change it, we can actually try to elaborate the answers for that. So we can extend these questions even further and say what prevents the application, look for what prevents the application to run faster, where it resides, and what should we do to make it stop holding us back. And we also have somewhat of the guidance of what should we use on all the stages. So the monitoring tools could actually tell us the direction where we should go to find that culprit, that bottleneck that prevents us to run faster. Profiling tools can get us the more concise and precise information on where exactly it resides. And your brain and your favorite IDE, which sometimes crashes on my laptop, can actually help you to fix that.
And I would also say that stack traces can also often be a good source of information if they're taken at the right point.
It is a sort of profiling, right?
It is.
I did this exception on this particular location in the code.
Or
1,000 exceptions there, which is even worse.
It is a type of profiling,
right.
Absolutely.
So when you start to deal with performance, you will have this hierarchy of the performance problems that you possibly have in your application. And you will realize that until you fix the high-level problems in your applications, those issues are masking the low-level ones, and there is no reason to fix the low-level issues before you fix the high-level ones, because you wouldn't get any measurable impact on your test scenario. So you wouldn't actually be able to say whether your fix changes something for the good or not. So for the science of that, there is something called top-down approach, which is a very famous term. When you say that you start with the very high-level characterization of your workload on the system level, how it interacts with your system there. Then you proceed, once you figure out that there's no problems there on the system level, you proceed to the application level. When you don't have the problems on the application level or obvious problems on the application level, you then go to the microarchitecture level and start to mess with all these things the hardware guys are like to mess with. I'm the hardware guy. I like to mess with this stuff. So with the advent of Java, it's getting a little bit complicated because Java sticks in between the system and the application. The JVMs are actually blended into the application space because it's hard to distinguish where the JVM, sometimes it's hard to distinguish where JVM ends and where the application starts. So you have to do this system JVM application microarchitecture level stuff. And when you think, when you see and look at that chart, it looks as if you fix all the system problems at once, then you fix all the JVM problems at once, then all the application at once, and you're done. So it looks like a waterfall, right? It isn't. The thing is, for each particular performance problem, you should go all the way from top to down. If you fix that problem, you have to get to square one and start over, characterizing from system level. Because you might change something that affects or highlights the issue on the system level. So instead of that waterfall thing there, the real performance work looks like this. You develop something, you conduct the experiments, you gather data, you analyze that data, propose the solution, code it up, and do that until your customer runs out of money. Or he's happy enough to pay you money, so you will just get out of here. So the important thing there is you should do that cycles only when your software passes the functional tests, because it's hard to quantify the performance of the broken application. What is the performance of the broken application anyway? If I can do 100 transactions per second but not do any successful work, does that count as the fast system? Probably not. It's important to do single change per cycle so that you are not missing the good things or bad things from your code. It's actually very frequent that you find yourself tempted to have these 10 patches, 10 performance changes that you want to test and get them through in one cycle. And you soon realize that you have masked some of the bad stuff in your code with the very good stuff that you have in that batch. And in this sense, you still have the performance improvement. Probably you have the performance improvement if you accept the entire batch, but not as good as if you will pick these changes one by one.
Yeah, it's hard to demux the winners from the losers.
Yeah.
In this case.
It's important to document the changes because I frequently find myself scratching my head and saying, well, I see this patch, it's really obvious, but what's it for? So if you're not documenting that, you're probably losing the valuable information from your experiments.
And I think if your test cycles are 2 hours in duration or longer, then there is a lot of pressure to apply more than one patch at a time. And I think it really behooves you to try to very much resist that particular pressure.
Right.
And also, if your cycles are 2 hours in duration, that means you're not going to do too many on a daily basis, which means that copious quantities of notes is often very helpful. Copying everything, saving everything, because you never know when you might want to go back and revisit something. And if a bench takes 2 hours or longer to run, you don't want to have to recover that data by rerunning that bench.
Right. So back down to that top-down approach, we know that we should characterize starting from the system level. And actually, if we characterize it on the system level, we have already the multiple decisions that we could make just by characterizing that stuff. So if we go ahead and just profile what's going on, not profile, monitor what's going on the CPU, you already have lots of things to test for. We actually have the greater version of this mind map in our backup slides, and you could probably get it once you get the slides from the DevOps. We will glance through that mind map as we go. This is our academical style of talk there. So let's apply this to our our test case, our demo here. So what we're going to do is go ahead and try to monitor the CPU of what this demo is doing, right?
Yeah, and note that this information is really readily available to you, and it's very cheap to global to you, and it's very cheap to collect. It's almost free, right? So we do have a lot of tools that will collect this information, but they tend to be, shall we say, expensive, and they tend to monitor a lot of things, so they put a lot of overhead on your system. This information, you can just get it almost instantly and analyze it almost instantly, so it's cheap and easy.
All right, so I got my JIT started. I start my stress test there.
Yeah, so we're back to normal there, okay.
Yeah. So we are doing stuff there.
Okay.
Let's do something like this.
So our entry point into the mind map is when our response times exceed our thresholds, because that's when we're going to try to start diagnosing what's happening inside our application. So what do we have here? Do you want to explain the columns left to right? Or?
Yeah, right. So this is the full system monitoring of what CPUs are doing there. So first column is the user time spent in the servicing the user code.
Yeah, this is MP stat, right?
Right.
You're saying.
You can do the same kind of thing with the VM stat, but the output of this tool is more verbose. So it's more helpful for us.
Okay,
the system time is the time spent servicing the kernel requests, or the time spent in the kernel there. The fourth column is I/O wait, as the time spent servicing I/O requests, and the interesting column is the last one, is the amount of time that CPU was spent idle.
Right.
So what is our problem with this particular test here?
So you just run it again. So the one thing that VM stat will give you that this one isn't giving you is, like, for instance, information about the length of the runnable queue. So one of the things I always like to ask, right, if I have idle CPU and my runnable queue is non-zero, it's non-zero length, that means I have threads there that are ready to run. There's nothing preventing them from running. There's apparently plenty of CPU available for them. Why are they not in there, soaking up those CPU cycles? What's keeping them out? All right. So, like, one of these very fundamental questions you need to ask.
So while this thing is running, I would try to dive in. And actually unfold what could be the problems on that CPU level. So let's just go over through the branches to cover the cases that are not covered directly by our demo, and we will get to the specific problem with our demo there. So if you have a lot of system time, you probably down to these four candidates there. Either it's network problems or network communication. Either it's the scheduling overheads, or it's just a plain swapping, or it's just some kernel bug sitting there and chewing up your CPU time. So if you are dealing with the network, there are tools to monitor that. You can use the Swiss Army knife of the performance guys, which is SAR on Unix machines. Alternative operation systems should have the similar facilities to actually provide you that performance data. Other specific tools are netstat, iptraf, whatnot. So what can you do if you are stuck with the networking problems? Well, you can probably go ahead in your application and try to reduce the traffic or the packet count that you're pumping through the system. Or you can go intensive way and try to compress the data that you are pushing through the network, hoping for the less throughput required, trading out the CPU time for that.
There's also some other patterns. So we have the revolving door anti-pattern, which is actually what I call a granularity mismatch. So you're shipping, basically with a packet, you have a certain volume of data that you can send, and it will consume that much space on the network, whether you fill it or not. And so if you send like 1 byte per packet, then that's a very inefficient use. And generally, that used to be an EJB problem where you'd say get across the network, and each time you'd get an int or something like that. And of course, one of the early solutions to that was the DTO, the data transfer object. And
Right.
that's like a bulking up technique.
Right, so this is the part of the bufferizations that you can do. You can also go for tuning up the IP stack in order to tune for BDP, which stands for bandwidth delay product. You can beef up the MTUs or actually reduce the MTUs. You can read lots of how-tos, how to do that on the
MTU? What's an MTU?
Maximum transfer unit.
Ah, yes, okay, that's packet size, right?
Right.
Yeah.
Or you might probably want to check your hardware there, because there are lots of examples, me included there, who were trying to optimize the performance of multi-tiered system, not realizing that they are dealing with a very, very bad Ethernet cables for one reason. We had the anecdotal example when we scratched our heads for 3 days trying to figure out the performance problem, only to realize that our database is connected to application server with a 10 megabit link.
Yeah, it's always fun.
Which makes all of the optimizations that you do on the lower levels kind of useless, because you're saturating that link and you're done. Or you might use the virtual interfaces so that your hypervisor will handle the network transfers between the guests without actually going for the real hardware. That would probably help both throughput and latency. You have to just to try it.
Yeah, if you can avoid using hardware, you're better off, right?
Yeah. So for scheduling our heads, this is the symptom of the unbalanced threading. Either your thread count is too high or it's too low. So you can try to differentiate those cases by looking at the context switches ratio.
Voluntary and involuntary?
And involuntary, yeah. The voluntary context switch is when the thread says, okay, I'm up to the blocking operation like network read or something like that, and I hand over my quanta to scheduler saying, I don't need it anymore, please do something else. And the voluntary is when I'm running out of my time quanta and my scheduler says, okay, now you're done, get out, some other threads wants to run. So you can actually segregate the parts when you have too many running threads that are able to run, or you just have lots of these blocking operations which trash the system.
So you're saying you've consumed your time quantum, and they're typically about, what is it, 10 milliseconds?
Yeah, it depends, yeah.
So on a single core, you're looking at about 100 natural context switches, involuntary context switches a second?
It turns out that most of the natural applications are actually blocking. So you have the dominance of the voluntary context switches.
Right.
But you can estimate that the rate of the voluntary context switches is somewhat in that ballpark, yeah.
So what's the cost of a context switch anyways?
In what units?
Yeah,
so it's like 10 to 4th of the CPU cycles to do the context switch. Depends on where you are switching up the thread. Also, you have these wake-up effects if the thread is waking up on the core and all the data is there on that NUMA node and has to bring it all back. Well,
yeah, so it's a very complex question, right? But
right.
You say maybe about 80,000 instructions, clocks or something.
Yeah, so my usual guess is 10 to the 4th, 10 to the 5 CPU cycles.
Yeah, for every context switch, right? That's what you
so
use,
it's
right?
really, really bad.
So if you're voluntary context switching quite frequently, then your CPU is going to be spending a lot of time actually doing nothing.
Right. Okay. So for swapping, you know what swapping is. For the Java, swapping is a killer, because even if the part of the heap is lying there in the swap, GC doesn't know that, and when it traverses the heap, it causes a lot of paging, because it wants to touch every single page in his heap. There is no production GC, up to my knowledge, that could actually get along with the swapping. So your goal when you're dealing with a Java application is to avoid swapping at all costs.
Absolutely.
Probably by trying to swap out the non-Java applications so you have the more headroom for Java heap. So there is the careful balance that you might want to tackle.
Well, we also find that a lot of things actually work better when you drop them into lower RAM, because they have different addressing schemes down there, which actually helps with performance.
Some of the Java implementations can have the side effect of locking pages in memory, preventing them from swapping at all. So for instance, large pages are getting locked into memory on the most operation systems, and they are not swappable because they are so huge, it would be terrible to swap them out. So you might have...
How big is a large page?
It depends. The normal page is like 4K, and you have the hardware support for the pages up to 1 gigabyte. So usual large pages that we use in our deployments is more like 48 megabytes.
48 megabytes, yeah.
So to swap that in on the hard drive,
Yeah.
you have to spend like 100 milliseconds to actually write it out,
Right.
which is bad.
And you also have other effects too. That gives you better object locality too, which means that you have quicker lookups.
Right. So other stuff, we rarely come up to this, but there sometimes the kernel code is not perfect. There are kernel bugs that may stir up in your face. So if you see the dominance of the system time and you don't know what that is, it is a good idea to go up to your system vendor or operation vendor and say, what the hell? Which means submit the bug report. Yeah, but you can tell whatever you want there. Interrupts, it's the usual stuff that you're interacting when you're interacting with devices, especially with the network. The significant trouble with the interrupts is that they are processed by the processors asynchronously, meaning that the process could stop everything it does and process the interrupts, which might affect the performance for real latency sensitive applications. But you also, on the other hand, you have the trouble if you dedicate one single processor to service all the interrupts in your system, so all other processors have it for free. You might run out of the computing power to process interrupts and then handicap your I/O performance, for that matter. So this is the interesting balancing that you need to get in your application. This is highly application specific there.
Yeah, and if your interrupt on the network doesn't get addressed very quickly, that can really knock out network performance.
You can step on the congestion protocol and your life will suck. Right. So the I/O waits. I/O waits is a very natural thing when you do the disk I/O. For the sum of the network file systems, actually the time that you spent communicating with the network is counted in that I/O wait. NFS is one of the examples there. Most of the network file systems are accounted in the system time there. And the I/O wait is more like going for the real hardware. Caching in the operation system does not count as the I/O wait, so if you service the request from the cache, you have a very low I/O wait.
Yeah, we find that systems that use NAS and NFS stat actually have a characteristic signature that you can use to identify these things.
You can use the tools like IOStat to actually see what's your disk throughput there. There are useful tips that if you are running into that problem, that probably your caching or bufferization is off for all these different reasons. Maybe the developers forgot to put the buffering there, or you run out of the physical memory to fit your buffers or caches in, or you just have very slow disks, and you might have to go and buy an SSD finally.
Yeah, SSDs are really game-changing.
Right. So caches are interesting because they are, in the most operation systems, allocated from the physical memory. So if you have lots of application consuming all the memory, you have less memory for the caches, which affects your I/O performance. And this is also the very careful balance you have to look around and find the optimal one. So if we go back to our application.
That's finished.
Oh, that's finished. All right.
Okay,
Why it's helping?
Start it up again. There we go. We can go and take a look at this.
Let's start it over. So now, with all this knowledge that we imposed on you, let's do the...
Yeah, they should be able to tell us what's wrong with this really quickly.
Right. So what is the problem that we are after here? What is the culprit? What way we should analyze? Should we go to figure out why user time is that much or that low? Who's for that?
Where's user time? That's
User
over
time
there,
is the first column, yeah.
There we go.
System time?
System time.
No. I/O wait?
I/O wait.
Right. Idle?
Idle.
Right. So we are going for the I/O wait, and the reason that the 50% for the I/O wait is really, really high. And if we go for the IO stat,
You said 15% is, what kind of threshold would you use in this case to differentiate between?
I would actually go for something like IOStat and see for this utilization column. So this is my block device SDB, and it utilized, if I get the more sample interval, I could actually see that it's 90% utilized, which is probably means it is the bottleneck.
Yeah, so that's, so you're in essence oversubscribed to disk in this particular case.
So how do we analyze it? First one, we can actually see there and see that this is my block device SDB, and some guy is reading from there. It's not writing, it's just reading. So we scratch our heads and try to figure this out. So to do that, we can go the different ways. We can ask the operation system of what is the disk activity there. We can actually do the strace to figure out what are the system calls that we are issuing in the operation systems. But we are Java guys here, so we can do...
Let's ask the Java application.
Yeah, and that's a Java application. So let's do something Java specific.
Okay. So I think what we have up here now is a btrace script, yeah?
Yeah.
And btrace, I don't know if anyone's heard of dtrace, right? It's like, you know, the operating system and a lot of the processes have been instrumented in such a way that you can get counter information out of them. In this case, what we're going to use is like, we're going to inject an agent into the JVM, and we're going to use that agent to instrument the, well, if we look at it here, we're going to go to, where's it? Data input stream?
Yeah.
And we're going to go into the method read, and we're going to say, let's instrument this so that we can actually now count how much data is coming out of here. But also, in the meanwhile, let's get a stack trace, right? So actually, who's actually responsible for calling this particular method here? Yeah. So we can understand what's going on here. So it's sort of a profile in this case. We're just going to inject an event-driven profile.
Right.
Here.
So I had already done that because my scenario is running, and so I can go ahead and consult what's there.
Right. And actually, if you go back, you can see that what we did was we set the property up as an MBean, and we're going to use the MBean viewer inside Visual VM. Oh yeah, see that annotation there makes this a particular property.
Okay.
And it makes that a property also. Okay. And so if we go back into the MBean view.
Yeah, and we can see
there.
This guy.
We can see, there's how much data this thing has been writing.
Reading.
Oh, sorry, reading?
Yeah.
Reading, writing?
So
same difference, right? And there's the stack trace. Unfortunately, this gets a little ugly. We didn't quite have time to whip up a plugin that would make this pretty.
But let's do this.
No problem. We can just whip this out into
This is like a voodoo magic, right?
Okay, fantastic. There's our stack trace. So it's not a complete thread dump, but it's just the one we need, right? And we can see we start from the bottom. That's jetty, 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 jetty. And now we get into application code, and then above it is all of this XML parsing, and we can see right here.
Right. So we can see the part of the code that actually acquires the stream, but we see the read all the way up that chain, right? So we have to look for these guys. So this is closing price file system data source. I wonder who named that class.
Gee, couldn't have been me.
Yeah. So it's there. And this is load, and this is our guy who reads something from disk, and we can immediately spot the problem. Not in that mess, but you can still spot the problem. I could probably do something like this.
What's this? It's this line here, right?
This is the acquiring the stream. So this is the guy who's reading most of the time. So what's the problem?
Somebody said it already. No buffer.
Yeah, so it's unbuffered. So let's try to say
buffered input stream. Yeah, all right. Get that out on the end there.
Yeah.
Get
so let's terminate these guys here. Start it over.
So in this case, we didn't go for a full profiler. We just went for something that answered the specific question that we wanted answered. And that's a technique that we use quite often. We'll just roll our own profilers because we know the question that we want to ask. And actually, a lot of these profilers, surprisingly enough, are durable enough to put into production systems.
Right. So what do we see now? The IO weight is gone.
Ah, look at that.
Yeah. Actually, I can see that because this flash drive of mine stops flashing.
You're using a flash drive?
Yes, I do.
Crazy.
I have an SSD, right?
Yeah, okay. Wasn't a flash drive an SSD?
Yeah, it was.
Okay. Anyways, that's a bit of a cheat, but okay. So you know, if we go back to our test results, let's go back to what Apache JMeter is telling us.
All right.
Aggregate report. There we go. Look at that. Isn't that beautiful?
Yeah, it is.
That's sweet. We're at 59 milliseconds, 58. Average time. We had a max of 977, so we're cooking along really nicely here. That's below our 100 millisecond threshold, isn't it?
Yeah, right.
So as far as
we
I'm
had reached
concerned,
our performance goals. So
I'm done.
Yep.
I get to go home. Unfortunately, you're a framework guy, right? Which means your goal is make it as fast as you possibly can,
right.
which means you're not done.
Yeah,
So I'll see you later.
my job is done when I'm saying, okay, I can't really do anything else there because
Right.
we are building the libraries and we don't really know how users will do that. Will use that library, so we have to optimize in advance for that. But look at that.
That's really wonderful what happens when you stop using a memory stick for a
So
database.
see that guy? He walks out of the room and the performance data is back to where it was, right?
What happened?
Get the
I was
invoice
done.
back.
I was
Get your
done.
invoice back.
I was done.
Yeah. You don't worth the money. I paid you. All right. So this is obviously bad. So we are not there yet. Let's figure out what's next.
Okay, let's go back to our, are we not going back to our metrics? Oh, no, we're going back to our slides.
Yeah,
of course.
right.
Our slides will tell us
So we fixed this IO weight problem finally. We need to go for the next step. Our performance goal is not reached yet. So we go forward. We hadn't explored the other way, the other branch there, which is idle. When you have a lot of idle, you are basically to do basic things that could be wrong. Either you don't have the enough software threads, meaning that you are running on the heavily threaded hardware, but you just don't have enough work to munch on, right? So the obvious answer is get more threads. Or if you can't make that application to use more threads, try to use the cores instead of hyperthreads on that machine, or do this all sorts of voodoo magic, which will try to beef up the single thread performance there.
Yeah, so one of the things about getting more threads is a lot of the projects we use actually have thread pools in them. And the nice thing about a thread pool is it actually allows us to control the level of saturation on the hardware, right? But so that we don't let our users thrash the hardware. That's the nice thing, but the bad thing about it is when we don't allow good saturation of the hardware, right? So that'll lead to high idle time. And that's one reason why we can actually end up with a lot of idle time. And there's
Right.
other issues too, like long calls to external systems, and there's a bunch of other ways
Right.
of actually getting
Right.
that type
So
of effect.
that is actually covered by this not enough runnable software threads. When you
Right.
actually have lots of threads, but all of them are waiting for something. So they could wait on logs, and this is the most significant part of that, or they can actually do the network IO and wait there. This is not covered on this mind map. I should probably put it there. So you, at that point, you start to explore the log-free algorithms or do the bulk network IO, etc. One of the strange, rare, but still surprising cases is the GC pauses when you can, well, it's not as rare, but you can, so the anecdotal evidence was like this. I had the application which is heavily threaded. I'm running it on the heavily threaded hardware. So I do the MP stat and I see a lot of idle. So my first guess is this is the scalability problem. I have a lock-in somewhere there. I do all sorts of profiling to find the logs. The logs are not there. I actually sieve through the source code to see whether I do have any sort of synchronization, and I don't have any there. It's perfectly parallel, but the idle is still high. And only then it hits me then I'm running the parallel GC, and there are way too less GC threads. So what happens, my application is running happily with all the CPUs it can have, then it steps on the stop the world, 4 lone GC threads wake up and try to garbage collect all that heap I have. The application at this point is stopped, so these guys are done with their work, and my applications again have all the system at its expense. But if you average this out, you will actually have a very high amount of idle time, because most of the time your system is idle. That 4 lone threads on the 80 core machine are just not allowed at all.
Yeah, and there's other strange situations you can get in with garbage collection, where we've had like perfectly parallel work running on multiple cores. And what we find is that the garbage collection was actually running too often, and not often enough that you would actually see it as a thread context switching issue, but often enough that it was actually causing the cores to idle. And in this case, tuning the garbage collector in one case took our application from a 70% utilization to a 70% utilization to a 99% utilization, which is the actual target we were looking for, by just having garbage collection run less frequently. And in this case, we had enough garbage collection threads that were fully utilizing all the cores.
Right. So let's run this again.
Run it again?
Yeah, just to remind what's going on there in the application. So it should be running now, right?
So we let them tell us what's wrong again?
Yeah, so what's wrong with this run? Is this user time what's wrong with this application?
I don't want to blast your eyes with the laser here.
Yep. System time is problematic. All right. I/O wait time is problematic. Idle time is problematic. Idle time is problematic. Okay, we can dive there.
Okay. So we're looking for thread behavior, and it's a very dominant thread behavior. And one of the more useful techniques of figuring out what your threads are up to, in this case, could be just as simple as taking a thread dump.
Right. So we can go ahead and do the thread dump. We had actually grouped our JIT threads in this group there.
Yeah, so what he's using is a plugin to Visual VM, which is called Thread Dump Analysis, which is a nice little tool. You can run it standalone or within Visual VM. The nice thing about running it in Visual VM, as you saw, is when you clicked on the thread dump, it would actually pop up this view. And you can actually even configure this view. In this case, what we did was we created our own extra category here so that we could find all of the JET threads that are actually running within the system. And we can get an analysis of what they're doing. Well, first thing what we want to do is we want to inventory the threads, right? So we want to say, okay, how many of them are there, right? Well, I got 2, 3, and 4. The other 2 are doing other things. Mm-hmm. What are they doing?
Yeah, so these 3 guys are obviously, so these guys are doing actually something useful.
Can we look at JMeter again?
Yeah, we can.
Okay. How busy is JMeter? We got like 760 users on this system. 780 now. It's like not even a stable number. It keeps going up and up and up. If we go back to Visual VM, being serviced by 3 application threads.
Yeah, which is bad. So
anybody have an idea of what might be wrong here? Undersized pool. That's the first guess. Wrong. No. Okay.
All right. So yes, this is undersized pool. So what we do with that, we try to beef it up. And this is
how big do we make it? It's hard to say, but what we can do, unless we get good statistics from the queue, or the pool itself, but we can do is we can make it extra big, and then we can do another thread dump and do some more analysis work, and then come back with a more reasonable size. We certainly don't want to make it big enough that we can let our users thrash the system. We had one experience where a very popular mobile company was dropping thousands of text messages on the floor because they were allowing, what was it, 34,000 threads to fire off under peak loads on a 64-way box. What do you think of that?
Yeah, it's bad.
That's bad.
That's my usual answer.
So
That's
the text
bad.
messages weren't actually getting through.
Right. So what do we put there?
Yeah, what do
50?
we put there? 50? 100?
100?
Your guess is as good as mine.
All right, so let's take the middle ground.
Yeah, sure. What do you do? We can come back.
It is the middle ground, right?
50, 100, 250 in the middle. Yeah,
Ah,
spoken
who
like a
cares?
Russian.
Yeah, it's a Russian arithmetic. Oh, no, you didn't.
What?
No.
Ah, okay.
Okay, so now we are running this test again.
You have 1 minute.
Yeah, I know. So the MP stat is there.
Wow, that looks like a huge improvement.
Yeah, that's huge.
Wow.
Right? I wonder.
You're brilliant. I like
Yep.
that.
Yeah. So that guess was wrong, right?
Not necessarily, was it?
Yeah. So how do we test it?
Thread dump. Let's monitor the
Thread
threads and
dump.
do the thread dump again. Yeah.
Oh no, not the Gmeter, the other guy.
Right? So we made a change to the system, and it seemingly didn't work. That doesn't mean it didn't work. It just means that maybe we exposed something else. And in this case, what we want to do is we want to go back and investigate and validate what's gone on so that we understand what's going on. Take the load off there. It'll be fine. Oops. Yikes.
That's okay.
And, so let's just do another thread dump. Let's see what's going on here. And, who knows what will appear, if anything.
Okay. So we now.
Oh, there we go.
No,
What
not
are you
yet.
doing?
So these are the Jetty thread pool. Now we have.
Oh, it's nice and big.
Yeah, it's nice and big, but we don't have the performance improvement. Why? We could actually go ahead and see what those guys are doing, but there is actually the better view in this tool when we can list the monitors, not the threads. And when we list the monitors, we could see.
Oh, I saw something.
Yeah,
big and red,
this
right?
is guy.
When it comes to performance, big, red, bad.
Right.
Look for the big red things. Focus there.
Right. So,
so
this
open up
is
the-
our bad monitor on which all threads are locking. So you don't
Open it
have.
up
Yeah. Let's
Come on now.
see.
and pick one. There you go. And if you tap down, you can see we have a clear pattern, right?
Right.
Same causal execution
Yeah.
path.
So it's the same stack trace, and
Yeah.
we know the method where it is.
Yeah.
Closing price system data source. I think I was there.
Are you there?
Yeah.
Okay.
Who actually wrote that method? It's just so problematic. So, and this is the lock.
There's our lock. Yeah, absolutely. So let's get rid of it.
Can
'Cause we actually
can
don't need it in this case. It's a read-only method.
Right. Okay. We will take that for granted. You shouldn't take that for granted.
Yeah, well,
All right. So we start Jetty, start the load test, and we run again.
Oh, that looked good.
I wonder if this wouldn't work. All right. Come on,
Okay.
Eddie. Come on, come on, come on. Sometimes it helps, actually.
Yeah, it's looking better,
Yeah, it's.
but it's still, user time is better. Right?
Yeah, so we are up
And idle
to
time is
60
okay.
is. So it's like guessing on the numbers at this point, but if we can actually do the larger sampling intervals, not the seconds, so we can. Oh, that's your. This is not a bug. This is just the presenter messing with us. But we can certainly say that
Oh,
they
sorry. I was hitting that. Okay,
Yeah.
I see that. Never mind. Oops.
Can I do that?
That wasn't intentional. No, you have to have the big bad one to be able to do
Okay.
that. You just got the tiny one.
All right, yeah. So the idle. Oh, come on. So the idle time is somewhat lower. We can actually argue that at this point our driver is the culprit because we can go for the visual VM and actually see that the threads are not blocking anywhere. Come on.
Okay, get rid of that bottom graph. There we go. Oh,
Yep, dump.
what do you want to look at?
I want to see the JT threads.
Okay.
And you see here, these guys are actually waiting on the input queue. So there are not lots of these JT threads. We don't need that much of the threads anymore because we are not blocking anywhere. But we set the maximum thread pool to the 250, and we aren't there. We have such low thread count, so that should be the load problem. So we can actually go ahead and say, hey there, stop. Come on, stop already.
It's almost there.
It's so slow. It drives my performance guts crazy.
Yeah, okay, there you go.
Right. So let's do this instead.
What? Oh, you're doubling the load.
Yeah.
Awesome. I haven't seen this part of the demo. Let's see what happens.
Yeah, you are too drunk.
I couldn't keep up with you. It's quite true.
Yeah.
Vodka.
And all I got is this tiny thing.
Yeah.
So this is our guy. So we incur more load on the system, and we are there in the huge user time.
Isn't that nice?
So
we just weren't putting enough load on the system to utilize all the CPU that was available. So
Right.
we have more capacity is what you're saying now.
Right.
So we can utilize it. Fantastic.
So I think at this point we need to take a break.
Yep.
Right?
So you guys can get coffeeed up and escape to the next talk. Oh, sorry, you have to come back, right?
Yeah.
Okay. Okay.
So let's take it, how much, 10 minutes?
I don't know. They're supposed to have 15, I think.
15 minutes. Okay, let's meet here in 15 minutes.
Yeah, so I have 10 after 3, so that's 25 after 3. We'll start up again. Okay?